Fusion Mobile, quality e-learning experience on the go.
My dearest, I hope you finished the assignment given to you on vectors. Today we'll be discussing equilibrium of forces. And in the discussion of equilibrium of forces, this is the particular topic that makes us create a balance of any parameter on the whole universe with respect to gravity. First, let's discuss the moment of force about a point. This moment about a point is defined as the product of force and the perpendicular distance from the point to the line of action of the force. What do we mean by that? If I have this to be a system, maybe with a meter rule, and somewhere here is my fulcrum, so that the meter rule can bounce to the left or the right, and here I set in a load, which is a force. The definition of moment says that is the product of this particular force and the distance here from this point to the point where the turning point effect is. So if I want to define moment mathematically, moment is equal to F times D, where D here is the perpendicular distance created. A couple is a system of two parallel and equal by opposite forces, not acting along the same line. Bringing it down to the turning effect or turning moment of a couple is the product of one of the forces and the perpendicular distance between the lines of action of the two forces. Now we come to the most important and interesting part of this topic, the principle of moments, which states that if a body is in equilibrium, then the sum of the clockwise turning moments of the body acting upon it about any point is equal to the sum of the anti-clockwise turning moments about the same point. What does that mean? If I am bringing it down with diagram, we'll say that we have this, for example, to be my system of meter rule, and here is my fulcrum, and over here I have a load, and this load is F1, and here I have another load, and this load is F2, such that F2 created a distance D2, while F1 created a distance D1. You know that in this system we'll have over here moment 1 and moment 2. If I'm going this way, this is clockwise moment to the fulcrum, while if I'm going this way, this is anti-clockwise moment to the fulcrum. Clockwise moment and anti-clockwise moment. The rule says that clockwise moment must be equal to anti-clockwise moment. So if I'm bringing it down here, that means that M1 must be equal to M2. And from definition of M1 and M2, we now have it that F1 D1 must be equal to F2 D2, and this is the major equations of moment. I would really like you to pick up any textbook by your side now and make a detailed study of moment of force. But most interestingly, if you can get it from Divine Touch Volume 1, is self-explanatory. Center of gravity of a body is defined as the point through which its resultant weight acts. Example: in human being, the center of gravity of a man is on his foot. If your center of gravity is at your head, that means we'll be falling with our head down while walking. There will be no balance. That brings us to the triangular force. And this states, when a body is in equilibrium under the action of three forces, all acting in the same plane, the three forces can be represented in magnitude and direction by the three sides of a triangle taken in order. What do we mean by that? The rule says that when a body is in equilibrium under the action of three forces, a certain body here is in equilibrium under the action of three forces. This is a force F1, this is another force F2, and this is another force F3. That's all acting in the same plane. The three forces can be represented in magnitude, direction, and sense by three sides of a triangle taken in order. That means I can represent this force in this way, such that I will have this to be F1, here F2, and this what? F3. They can be represented with a single triangle. Stability of a body. A body said to be in stable equilibrium when the body in position of stable equilibrium when a receiving or is receiving a slight displacement, it tends to return to its original position. What do we mean by that on the slide? When you have a funnel, for example, and you place the funnel down with the conic parts down, the parts with higher base, you will notice that when you push the funnel, it will tend to go back to its point. For example, if I have this to be my funnel, when I give it a push, it will tend to go back to its position. At this point, we'll say that this funnel is unstable equilibrium. It is unstable equilibrium. While when it is this way, you notice that any little push given to it, it will fall off from the normal position that it is now. At this moment, we said it is at an equilibrium which is unstable. By definition, a body is said to be in position of unstable equilibrium when, on receiving a slight displacement, it tends to move further away from its original position. While neutral, we get that when the body decides to roll with the part of the funnel. At this point, the funnel can only roll. It will not fall out or it will not fall back. At this moment, we say that a body is neutral equilibrium when, on receiving a slight displacement, it tends to come to rest in its new position. At that point, it will roll around only, and that is why we say that spherical bodies are constantly in neutral equilibrium. Now we move over to equilibrium in fluids. And first we discuss Archimedes' principle, which states that when an object is wholly or partially immersed in a fluid, it experiences a loss in weight or an upthrust which is equal to the weight of the fluid dispersed by the object. What do we mean by that? If I have this to be a bucket, and here is another bucket, collection bucket, and this bucket is filled to the brim, here it is filled to the brim, and all of a sudden I dropped a ball inside this bucket, such that water from the bucket will keep creeping out this way. When I collect this water from the collection bowl down, you'll notice that the water from that collection bowl will be equal to the weight of this object, or the apparent loss of weight of this object when it experiences that. We say that that apparent loss in weight is called upthrust, and that upthrust is equal to the weight of water collected here. If you want to notice upthrust in real life, I don't know whether you've been to the stream before to fetch water. When you are carrying the bucket of water in the stream, it seems that the water is not heavy, but when you come out in space, what happens? The weightness of the water will come out. So we said that in water or in fluid, there is an apparent loss in weight, and this apparent loss in weight, upthrust, is equal to the weight of the fluid dispersed. Principle of flotation. This states that a floating body displaces its own weight of the liquid in which it floats, or a body floats when the upthrust exerted upon it by the fluid is equal to the weight of the body. Density and upthrust. Here, first of all, I want to mention the instruments. A hydrometer is an instrument used in measuring the density of fluid. Now, the question is, what is density? Density is the ratio of the mass of a body to the volume of the body. Mathematically, density, which is given as rho, is equal to mass of the body all over its volume. This is density. If you want to know the density of Sayudi Jesus, measure the mass of Sayudi Jesus and divide it by the volume which Sayudi Jesus occupy, and that is the density of Sayudi Jesus. And a hydrometer is used in measuring this density. While upthrust is the apparent loss in weight, what does that mean? Upthrust is equal to weight in air minus weight in fluid. Since in fluid it seems there is no weight, and in air there is real weight, the subtraction from weight in air gives us the apparent loss of the weight, and that is what? Upthrust. From there, we'll talk about relative density. In density, we said it's mass of the volume, or mass over volume. But in relative density, we have a mass comparing to the mass of water. Relative density, RD, is the ratio of the mass of substance to the mass of equal volume of water. I repeat, relative density is the ratio of the mass of substance to the mass of equal volume of water. Now I would like you to pick up your textbook and have a detailed study immediately on relative density. From there, we'll now move into pressure in fluids. Look at that wonderful diagram there. The spouting can, the water, hose for jets, weakest jets, strongest jets. We will discuss all this in level as we move into the next topic. But before then, have a wonderful reading on relative density, and I want you to teach me when we meet again while I teach you pressure in fluids. Have a wonderful time, my dearest.